Hey, well, welcome everybody. Appreciate everybody showing up for this presentation on quantum sensors. I'm very fortunate to have been able to meet and or work with some fine people that came out of the Womanium project and their interest in engaging industry like the U.S. Naval Nuclear Laboratory to sponsor these projects. So tonight we will have actually two presentations. First presentation will be by Dr. Erica Sturm, and following that, Anjolie Tuazon and myself will have the second presentation. So, Erica, I'll turn it over to you if you want to introduce yourself and fire up your slides when you're ready.
Yeah. Um, Hello, everyone. Thank you for coming. My name is Erica Sturm. I did my PhD work here in Chicago in theoretical chemistry, and then I pivoted over to condensed matter at Brookhaven National Lab, where we worked on machine learning for condensed matter systems, specifically the Kondo problem. And since then, I discovered quantum computing, and I said, gee, that sounds like it's right up my alley. So I got involved in the Womanium program, and I was fortunate enough to be selected to work at a fellowship program in collaboration with the Naval Nuclear Laboratory, just like Ron and Anjolie. And with that, I will share my slides, and we can start the party. So give me just a moment. Of course, I moved the windows in the wrong place. That's good. All right. Why is this not working? Oh, there it is. Okay, here we go. Please speak up if the slides are not working, because I will not be able to tell.
I see them.
Okay, thank you. So with that, today I will be discussing the science of quantum sensing, specifically with nitrogen vacancy centers. As stated, this work was as part of a fellowship opportunity with the Womanium Foundation, specifically their quantum department. And this is with collaboration with the Naval Nuclear Laboratory, specifically with Dr. Brian McDermott and Dr. Jesse Holmes with those institutions. So let's get started. So the first thing I want to discuss is why should we look at quantum sensing in general? Why quantum sensing? What's wrong with regular sensing? Is it just a fad? Why should we do this? And the answer is because quantum sensors may offer many, many benefits beyond what classical sensors offers. Some of them are enumerated here. For example, they have an improved signal to noise ratio in some instances. So this means your signal will be more clear and there's less cleanup to do. There may be a smaller physical footprint, and this translates directly to greater portability. Instead of lugging around an enormous sensor, you can lug around perhaps only a couple of atoms inside a system that's for input and output. And this is much easier to drag around. You could have them in your car, for instance, instead of having an entire truck dedicated to them. And they may have broader sensitivity ranges and therefore be able to detect things beyond classical limitations. And what this means is we might be coming up against, if you were sensing a classical uh, um, feature, if you were looking at a classical feature for the purpose of sensing any detections in it, you may actually be able to go beyond and beyond those classical limits because you are looking at the quantum limit. And so this is an improved sensitivity. And therefore, these are of great interest not only to the private sector, but the public sector as well. This could be used in all sorts of things. For example, GPS, thermal sensing, radio sensing, any kind of electromagnetic radiation. These are all things that can be detected by various quantum sensors. But instead of talking about all of the quantum sensing capabilities out there, I just wanted to focus today on the nitrogen vacancy centers within diamonds. And the reasons for that are multifold. For one thing, nitrogen vacancy centers are coherent, even at high temperatures or under extreme pressure. This is in contrast to many classical sensors, which tend to break down once you get beyond certain temperatures. Diamond is extremely stable and it will melt until you reach truly excessive temperatures. So these can go into places where perhaps classical sensors will break down or melt, like their interstitial wires would melt, and diamond won't, which is kind of a nice feature. Furthermore, they can also go down to very cold temperatures, so you don't have to lug around those terrible cryostats, which other sensors may need to keep away ambient noise. These sensors, depending on how they are calibrated and set up, can detect everything from temperature and strain, and as mentioned earlier, electromagnetic radiation of several different varieties in different frequency ranges, depending on how you set your system up. And the final point, and this is very important, and we're going to see a little bit of this in the next talk, would be optical readout makes these very straightforward. And the reason for that is because this is a mature technology. We have been using optical readout for I would argue decades at this point. So it is a mature technology capable of being used by many people without too much fuss and bother because it's become commercialized at this point. What I mean by, I should have said this, optical readout just means that it's happening in the visual spectrum. We can actually see this. Unlike, say, X-rays or microwaves, optical readout is like green and red light, which you and I can see. So this makes it very easy to detect when something is happening, even with the naked eye, although that's not recommended because you will burn your eyes out. But hey, you could still see it. But anyway, so that's great. I'm motivated. But what is it and how can we use it? Well, I'm so glad you asked. This is it at the atomic level. What you are seeing here is a molecular diagram pulled from some software I was using called the Atomic Simulation Environment. So what you're looking at here, the gray spheres are carbon atoms. Each one is a separate nucleus. And these form the diamond lattice. They are in what's known as the rhombohedral configuration. This is the same as it would be in geology. So what makes the nitrogen vacancy center within the diamond? Well, there's a blue nitrogen here. This is represented in blue. This is a nitrogen atom, and this is a substitution. So instead of carbon, we've just taken the element right next door on the periodic table and swapped it in. So that's in blue here. And then the vacancy part, as you may imagine, is empty. This is a missing atom, and that's represented here with kind of a green circle, but actually there's nothing there. That's just a placeholder for the sake of visualization. So this is the nitrogen vacancy center, and we're missing one last piece. Oh, I should say the black bars are the chemical bonds. These are covalent bonds that make the diamond so strong. This is why it is the hardest substance or natural substance that we know about. And the remaining bonds that would have been attached to that carbon are still oriented in that direction. They still point to it. There's just nothing to attach to. So they're just kind of flopping around in there, in that vacancy cavity. The last thing that we're missing to make this of interest to the quantum computing and quantum sensing communities is a missing electron. This is usually donated by somewhere in the carbon lattice. It does not matter where it comes from, provided that it exists and it bops around inside that cavity. Once it's in there, that's all we care about. Where it comes from, why it goes there, that is beyond the scope of what we are studying today. But once it's in there, it is this overall anionizes the system. That is to say, it gains a negative charge. So instead of becoming just a nitrogen vacancy center, we now call this NV minus or anionic nitrogen vacancy. And sometimes in the literature, they just call it a nitrogen vacancy because this is the most common way to see the system. So I may use those terms interchangeably, but it is understood that at all times, this will be in its anionic state, which is to say, there is this electron present. And it is, in fact, this electron and its spin, its inherent quantum mechanical spin, coupling with that of the nitrogen nucleus that make this a qubit. That is what is used in quantum computing as well as quantum sensing. So that's the physical system. And that's great. But computers don't care for this. Computers don't want to have this kind of input. They prefer things with numbers and equations. So how do we take this information and translate it into an equation? Well, the first thing is we have to understand what is happening mathematically with this system. We just looked at the physical system, but what does that mean when we talk about what happens at mathematical level? And that's where this comes in. This is called an electronic state diagram, and it's basically different levels that electrons can populate. If you remember from your high school physics class and you had to populate a bunch of concentric rings with electrons, you would start at the innermost level and populate upwards. In a similar capacity, that's what you're looking at here. So along the non-existent y-axis of this graph would be increasing energy. So you start at the bottom and fill up. I want to note that this is not to scale. This is a cartoon model just for the sake of demonstration. In reality, these levels are very, very close together, and you need special equipment to delineate which level you are populating. But for right now, this will do. So there are three main states here, and they are in blue: the 3A2 state, the 3E state, and the 1A1 state. These are from group theory, so we're not going to go too much into that, but these are the labels that we use in the chemistry community to talk about these things, and they are based in the mathematics of group theory. But you might be asking, okay, but what are those orange bars? Those orange bars are the result of the electrons interacting with other electrons in the system, and this creates a magnetic dipole. As an analogy, you can think of this as having two magnets, and when they interact with each other, you kind of create like a warped magnetic field. And you can actually, if you have like a third magnet oriented between them, it will align so that it has its north pole pointed at other south poles, and vice versa. It's south pointed at norths. And the point is that this will cause the blue levels to split into their sublevels. And that's what we're seeing here. These are the quantum spin numbers for an electron given by the letter MS. 0, -1, and 1. And that is because this system has an overall charge of 1 due to the extra electron that has populated this center. So that's what you're seeing here.
Philadelphia passengers.
Sorry, is there a question?
Two.
Okay.
I think someone just I muted them.
Okay, thank you. So the three main states will split into these substates, these triplet states, but only those two triplet states, the 3A2 and the 3E. They will both split into triplets. This is what makes them triplets, but the singlet state, the 1A1, will not split. It's a singlet. It has a single level. But we're not done. Oh, right. And you can photo excite this using green light, visual green light. So you and I can see this. It occurs at 532 nanometers. And it will de-excite or relax back down to its ground state energy at a frequency of 637 nanometers. This is red light. And again, we can see this. There is another secret other way for it to decay, and this is known as an intersystem crossing. What ends up happening is once it's excited, once you have moved from the 3A2 ground state to the excited 3E state, what will happen is, under the right circumstances, it may decay down, not back down to the triplet state, but rather to the singlet state. And this is a non-spin conserving process, so the spin has to flip, and that is why the plus and -1 states in yellow here at the top, that's why these are preferred with heavier arrows. It can also happen from this level, it is just less likely. So if it is going to go through this alternative decay pathway, it will most likely come from one of these. And then it will continue to decay back to the ground state. Nothing ever wants to stay permanently excited. It's like you would never want to keep running your whole life. Eventually you want to sit down. So no matter what, regardless of whether it's an optical emission in the red frequency light range, or if it's undergoing this intersystem crossing, either way, it will eventually reach its ground state again. But there's more to this picture than just the fine structure in yellow. There's also hyperfine structure. This is due to interactions between not just electrons, but also like the fine structure is, but this is due to interactions between electrons and the nuclear spin of the nitrogen, of that substitutional defect within the diamond. So here I've shown the ground state. Again, the 3A2, all I did was take this part of the diagram and blow it up even bigger for the purposes of demonstration. And now we see there's even more splitting. So not only do the electron-electron interactions cause splitting, but electron-nuclear interactions cause splitting. And that's what we're seeing here. So these are the purple is due to a nuclear quadrupole. This is the nuclear spin interacting with the general electron environment that it's sitting in. And then the hyperfine interaction has a much, much more kind of deep cause. But for our purposes, this this is the degeneracy in the levels and the splitting can be seen if you create a static external magnetic field. So all of this together creates quite a lot of levels for us to populate. And at any given moment, the electrons in the system can occupy any one of these. You may say, oh, well, they're here. Yeah, but which subcase are they in? The number of electrons doesn't change. It's just a question of how specific do you want to get when you are labeling them. If all you need to do is label it, it's a ground state electron, maybe that's enough to just say it's 3A2, but you can get more specific, and that is what these additional labels are enabling us to do. We can see this granularity now. Okay, so that's kind of what's going on from a physical perspective, but we still haven't actually explained how we get this into a computer. I said that's what we were going to do, but all this time I've been talking about energy levels. Well, the thing about energy levels is that, they take on numbers, and we can put all of this stuff here into an equation. So I want to draw your attention in particular to D, the magnetic dipole in red. This is what gives us the fine structure. This is electron-electron interactions. And I want to draw your attentions to Q and A. These are Q is the nuclear electron interaction, and A is a more fundamental physical effect due to the nature of the nucleus itself of the nitrogen, and that is beyond the scope of today's discussion, but that's where it comes from. So those three variables I just mentioned, we can collect those and put those into what's known as a Hamiltonian. This is not unlike the Hamiltonian you see in your standard Schrodinger equation. It is explaining if you solve this equation for this ordinary differential equation, when you solve it, you get the eigenvalue, which is the energy for the system. And therefore, the eigenspectra tells you the energy levels that are possible to be reached and how much you need to access those energy levels, etc. It works just like the Schrodinger equation. It's just a different equation than kinetic and potential energy. So to reiterate, the D is the electron-electron magnetic dipolar interaction. This creates the fine structure that we saw, those yellow bars. And the Zeeman effect, which is to say the application of an external magnetic field can lift the degeneracy between the plus and minus one states. Q is the nuclear quadrupole moment. This is basically an effective torque of the spin of the nucleus of the nitrogen with the external electromagnetic field that is due to the electrons around it. So these two things together create some kind of torque as the nucleus is spinning in spikes, and that's represented by Q. And A is, this has to do with the nucleus itself, and it does have parallel and axial components. Again, the same external magnetic field application would also cause the degeneracies there to lift. And all of that comes together in this Hamiltonian expression here. So here we have D, Q, and A. These are constants. These are scalar numbers. We can measure them in the lab and plug them in. The rest of these equations here are operators, just like your regular application. Now, this equation works at ambient temperatures. It does not work at cryogenic temperatures, which is beyond the scope of today's discussion. But this would apply both for the ground state and the excited state. And if you can solve this, you now can recreate in the computer. You can recreate those energy levels that I was showing a slide ago. That's what this equation will give us. So this is something we can put into a computer. That's great. Now, what does this have to do with sensing? Well, if the system was never perturbed and it was left alone forever, it would never change, and this equation would always, always be true. We could solve this equation, and we could know where the electrons exist at what levels forever. But no system is ever isolated, right? That's not possible. And in fact, we're going to use that to our advantage because that's what quantum sensing is. We are measuring the changes in something. So how does the sensing part work? This is the same diagram as before, but I've cut out a little bit of the hyperfine structure because depending on what you are sensing, maybe the hyperfine structure is a little too much detail. After all, if you don't need the extra detail, don't bother computing it, you are wasting resources. Sometimes good enough is good enough, and in this case, that's what I've chosen to showcase because it is easier to see. So, how do we initialize a nitrogen vacancy center for sensing? How do we do that? The first step is to optically pump the system from its ground state 3A2 up to 3E. So all we're doing is we're taking a green light and shining it at the vacancy center. And this is typically done with lasers because we want to make sure we're very precise when we're shooting at a diamond. After all, they're not using, enormous diamonds. They're using very small ones. So this is done with a laser. This is a spin conserving process, which means the quantum spin numbers do not change. If it's spin up, it stays spin up. So what is in this diagram here, if you're at spin level 0, you're going to go to 0. If you're at -1, you're going to go to -1, 1 to 1. That's a spin conserving process. We're still going from 3A2 to 3E, but the sublevel, the kind of more precise language would be, we're going from one of these ground levels to one of these excited levels. Now, earlier I mentioned there are 2 decay pathways. The first is here in red. This is the radiative decay. This is red light in the visual spectrum. Or we can do the other thing, which is 2B, and that's in black on the right-hand side of the diagram. So if we can, as I mentioned earlier, but I will reiterate, it is while we can undergo an intersystem crossing from any one of these 3 levels, it is most common to go from one of the top 2. That's just more common. Once we're at this level, it is going to preferentially decay down to this this ground state here of ms equals 0. That is to say, the intrinsic spin of the electron will be 0. And that's important because before we start the experiment, each one of these has an equal probability of being populated, assuming that you don't have an external magnetic field. But if that's what's going on, then you can't really use it as a sensor, because the whole point of a sensor is that you want to measure a change. You want to say, okay, if this is your baseline, how much did you change? But if you start in any one of these 3, you won't be able to measure that because you don't know what you started with. So we have to have a place to start from that we know without shadow of a doubt. And that's why this intersystem crossing pathway is so important, because it will almost certainly decay down to this level preferentially. It is possible for it to go to these other 2. However, by continuing to this process of providing green light on it, eventually we can guarantee that any of the population density will in fact occupy this lowest level. So as long as we shine the light long enough, it will do this. And then we know for a fact that we are starting from the same place every single time. And then once we have initialized our sensor, then we can use it to measure whatever it is we wish to measure, whether it's temperature, pressure, strain, a magnetic field, whatever. And that is done by measuring how the change between this ground level and one of these upper levels changes. Because if it's normally, say, this many units apart, and then we apply something like strain, maybe now they're this far apart, we can measure this. Or maybe we apply a magnetic field and it crunches down a little bit. This is also something we can measure. So we measure the change in how much energy it takes to go from that MS0 state to an MS plus or minus 1 state. And that is how the sensing is executed and accomplished. I want to mention at this point the very generous time of Dr. Harry Pottle from the National Energy and Technology Laboratory in Pennsylvania. He was very kind and explained this process to me in great detail. So I wish to thank him for his patience and his generosity. So thank you. Okay, so before I move on to what's next, I want to say, okay, so we've set up our system. We have our ground state Hamiltonian, which would be true forever if it was never perturbed. But here we are perturbing it. We are applying a strain, a magnetic field, an electronic field. Something is happening. How do we measure that mathematically? How do we put that into a computer? We use something called the Lindblad equation. The Lindblad equation is an example of a master equation. In particular, it is a quantum master equation. And this is how we measure non-reversible or irreversible or non-unitary dynamics. That is to say, things that do not stay constant in time. And that this equation enables us to do that. So we're no longer using the Schrodinger equation because the Schrodinger equation assumes no perturbations. This is a more generic form of an equation that can handle both time-dependent and time-independent cases for evolution. And it looks like this. So let's talk about this for a moment. This is the density matrix, rho, and it has the standard definition that we've all seen before, where it's the Ket-Bra notation. And this little dot up here means the first derivative with respect to time. So what we are really looking at is the change in the electronic density with respect to time. Put another way, we are saying, where is it most likely for the electron to be as we move forward in time? That is what we are looking at here. And this is accomplished by this, at first glance, I will admit it's a little intimidating, but it's really not that bad. We'll start at the beginning here. This is the Hamiltonian expression that we saw 2 slides ago. So we just take that whole equation and plug it in here, and that's it. So I didn't want to repeat all that. It would take a lot of space on the page, but that's all it is. You just plug and play. This is the commuting operation here with the density operator, which again is given here. And then we have this part here. This is the non-unitary part. This is the evolution in time because, as you can see, this all depends on time. And this overall is an ordinary differential equation. And we can set up computers to solve this, which is very nice because I don't want to solve this by hand. So what you're looking at here, these are rate coefficients. These are scalar values, and they the size of them, if they are larger in magnitude, that means a transition is more likely to occur. And if they're smaller, they're less likely to occur. And then these Lindblad operators are simply measured, they are projections from the final to initial states. Just like any other density matrix expression. So you start in the final state with your ket here. You take the inner product with a bra, the outer product with a bra, and that tells you the probability of transition from that final state to that initial state, whatever they are. So if you only have 3 states under consideration, you will have 3 Lindblad operation. You combine all the final states with all the initial, and you get your array of all possible combinations for your Lindblad operators. So if you have 3 places to end up, 3 final potential places and 3 initial places, then you will have 9 in total, right? You can decay from any one of the 3 down to any one of the 3. That is 9 combinations. And that and their strength is controlled by K. And that's all you're really seeing here. These curly brackets are the anti-commuter. And there are many established mathematical tools that are used to do this. We will not be discussing them, but they are readily available. They have been published many times over, and there are standard ways to solve all of these equations that even come in pre-programmed packages, which is actually what we were trying to do. So in collaboration with the Naval Nuclear Laboratory, Womanium, my job was to develop a software suite where all of this could be modeled by anybody. You see, one of the snags in the research community right now is that everybody and their sibling has a different question. This group is modeling temperature. This group is modeling strain. This one's modeling what happens if you hit it with this kind of an oscillating electromagnetic field. But what if you want to just have something kind of on the more basic side and just see how it evolves in time? Now what? Well, that's what we wanted to do. We wanted to come up with a software suite where you could ask the computer, here's what I want to do. Now run the simulation for me, and what can I expect? And that's what we were trying to set up. So we thought it would be nice to have a different way to say, okay, I want to model pressure changes, or I want to model electromagnetic changes and see how those evolve in time. Or maybe we wanted to see how 2 effects at once would influence the population densities. How would that evolve in time? So ultimately, we are pursuing this. We will be using this in a user-friendly way. We will be developing this for to be user-friendly using a Jupyter platform, which is a kind of an interactive way to work with Python. And specifically, we were going to use the software library of Qtip, which is Quantum Toolbox in Python, which is uniquely designed for the evolution of quantum systems, such as this one. And the hope was that the user could input some their parameters and hit run, and a few minutes later come back and get a pretty good approximation to what they could expect in reality. And with that, I would like to thank you for your attention. And I've been told that we will do all questions at the end because we want to move on to our next talk, where the physical implementation of what I've just been talking about from the theory side. Again, I want to thank the Womanium Foundation for sponsoring this opportunity, and I want to thank the Naval Nuclear Laboratory for their collaboration, insight, and guidance for this project. And with that, I will hand it over to Ron and Anjolie. Thank you very much for your time.
Thank you.
Erica. So our next presentation is a research project that Anjolie and myself teamed up on. And it was basically to actually design some physical hardware. So, but before we get started, Anjolie, would you like to introduce yourself?
Yes. So hi, I'm Anjolie, and I'm a junior undergraduate at the University of Maryland studying physics and electrical engineering. And I'm currently with the Center for Quantum Networks doing quantum sensing and doing super resolution sensing with spatial mode sorters.
Okay, and I'm Ron Schreiner. A lot of you here already know who I am. I've been in the technology business a long time. Just recently got involved with quantum computing and quantum technology, and again, as a result of the Womanium project, I was fortunate enough to be asked to join this project. So thank you for your attention. I'm going to go ahead and do a share here. And we're going to do so hopefully everybody can see this slide, hardware design challenge.
Yes, I can see it.
Okay. So once again, this was a project that was sponsored by the U.S. Naval Nuclear Laboratory, and it was basically to build some art or to do some research to design some hardware. And okay, there we go.
Okay, so the goal of this project was to design a low-cost handheld quantum sensor device based off of the diamond nitrogen vacancy centers that Erica just talked about. And so our design, the goal is for the design to be used as an educational tool to teach quantum hardware technologies, because we do have an abundance of like online courses and material, but there's not a lot of demos and hands-on activities that we could use to teach these quantum concepts.
So we were given specific requirements for this project. I'm just going to touch on a couple of them here. Anjolie can talk about some of the other ones. We had a target price to be able to build this hardware at $1,000 or less, which is pretty daunting once you start studying this, because you look at all the we reviewed close to 20 research papers on how you might build hardware to do this. And in a lot of cases, they're doing the experiment in a very well-equipped laboratory with diagnostic equipment that's just off the scale. You're talking thousands and thousands of dollars just for the diagnostic stuff. So being tasked with trying to build a functional device for less than $1,000 was pretty challenging. The other thing is it had to be small and light enough so that it could be carried around by hand, and something that would be very useful in an educational environment again, or a classroom. The other major thing was they wanted to be able to use as many off-the-shelf commodity parts as possible. Uh, Anything you want to add there?
And yeah, so the design, our design should be understandable to a wide audience so that like teachers or like students or hobbyists are able to build the sensor themselves.
Oh, and so the device we're to design is referred to as ODMR, optically detected magnetic resonance. So our specific design was tasked at being able to measure magnetic fields. Move on. So there's a number of things we had to do, and here's kind of a list of them. Some of the things that I thought were very interesting was building a vocabulary or a dictionary, and using, some pretty standard engineering tools to make decisions and for different things like uh, what sort of configuration should it be in? Is it going to be completely self-contained, or is it okay to have it work with like a laptop or a tablet, uh, that sort of thing. But we compiled a lot of information, and again, there's a bunch of stuff that was prelude to actually starting the design is listed here. Let's move on.
Okay, so one of the things that we made were decision trees to help us make decisions on like the type of diamond that we should be using. And so all of these diamonds listed here were from all of the literature that we reviewed. And so there were a lot of different cuts and coatings and sizes of these diamonds, but ultimately we ended up choosing just a basic diamond from element 6, which costed $180. But if we had more money, like, or if there was a way for us to like reduce the cost more and get a more custom diamond, then we would do that. But for now, we are just sticking with the generic diamond from element 6.
Yeah, and that diamond is to give you some sort of idea of what it's like. It's 3 millimeters by 3 millimeters by 1 millimeter thick, so it's fairly small. And there's I'm sure all the ones listed here are synthetic diamonds. The one we were looking at was specifically built using something called a chemical vapor deposition process, which all by itself is a fascinating technology, and how they can grow diamonds in these plasma-like chambers.
But yeah, so we compared the diamonds from each implementation, looked at their pros and cons, and some of the challenges that the authors had with the specific diamond. But yeah, like ultimately we chose to stick with the diamond from element 6, which is about $175.
Yeah, and this slide's a little out of date because last time I checked, the price on that diamond had gone up a bit. But again, got to remember our budget. We didn't. We basically had to consider that the cost of the diamond was going to affect the project. Here's another decision tree on, again, what would the configuration of the device be with regards to command and control measurement. Is somebody got a question, or can you mute? Okay. So the device would need to be you would need to be able to control it and command it to do things, and then you would also need to be able to extract the measurements from it. And so what this decision tree kind of led us to is uh, is to basically to keep the size of the device small and again to keep the cost down, is to utilize communications like with like a laptop or a tablet via USB cable. That solves a lot of the problems as far as you got a laptop, then you got a display device, you got a keyboard, you got to basically just build a protocol to command the device and read the measurements back over the USB connection. But this is kind of some of the things we went through in the research process to get to a design launching point. Lots of things learned on the way. Obviously, we had to learn how ODMR works, and thanks again to Erica and her presentation. You guys all have a good understanding of how nitrogen vacancy centers and diamond crystal behave, and that's what allows us to use these diamond crystals with the appropriate apparatus to operate in the ODMR mode. But some of the other things that we had to learn about, a lot of the designs that we studied used green light to energize the crystal, but also you use microwave pulses to modify. Basically, you're modifying the center frequency effectively of the green light, and that gives you the ability to really dial in how much energy you pump into the crystal in the first step. We also found that there's an analogy to the DiVincenzo criteria for quantum qubits that doesn't have as many rules, but basically it's a similar criteria that defines what a sensor would be. And anything else there, Anjolie?
Yeah, so we learned that there were like many types of different designs that we could go about this, and different types of performance that went with those designs as well. And so for my design, I also had to learn how to use a Smith chart for impedance matching, which took me a while, but it was definitely a good experience.
So are Smith charts now your favorite thing?
Yes, I love them.
Okay, just so Smith charts are found in radio radio and transmission theory courses if you're into electronics, and they help you understand how energy can go down a coax cable or up an antenna, and gives you a way of plotting on a Smith chart what the impedance of any of a system might be. So first design that we come to is basically a completely self-contained design. And again, some of our design goals having to do with keeping the cost down was one thing, but we also had to make this design so that it could be built by anybody who wanted to take the time to give it a shot. So again, one of the important things was off the shelf components. The other thing is if we needed a custom housing, it's almost better with the technology we have today to just design it for something that you can 3D print. So that's what you're seeing here is basically the case, which was actually rendered on Tinkercad. So these are actually parts you could send to a 3D printer and just have them printed. Now, a lot of people said, well, no, I don't have a 3D printer. Well, you find out that like in my area, a number of libraries, for example, have 3D printers now. There's places you can get access to them, and then if you're really hardcore, though, they're not that expensive these days. Nothing in this particular mechanical design would require any, would not require a high-end 3D printer at all. A couple of things you see here is there's an electronics bay on the top here. This would be populated by a couple of Arduino Nanos. One would be responsible for communications back to a laptop or desktop or some other type of computer. Another one would be used to control the precise timing that you're going to need. And the middle board here, it would be most likely the driver board. On this board would be components that would allow you to create a radio frequency, a microwave source that would be variable. You have to be able to generate not only a pulse of microwave, but be able to sweep the frequency over a specific range. And again, some of that has to do with, you can think of it as effectively moving the center frequency of the green light. Now in this rendering, what we have here, you can get the green light from anywhere. If you can get it from a cheap green LED, great. If a cheap green LED doesn't work, then a solid state green laser will be your next step. In this initial design, I had come up with a light pipe, this conical shaped light pipe, and its job is to bring the green light down to the diamond crystal, which is this little tiny thing below this this component that looks like a microscope bottom lens. That's because that's what it would probably be. Here's a block diagram for this implementation. Again, yeah, you have some sort of computing device just off the shelf, connected via USB cable to the communications board, which is tightly coupled to the timing board. The timing board controls the LED driver. One thing we did notice in some of the documentation is that an LED by itself might be right at the edge of a usability limit. So one thing that we would do with the driver is we will try to operate that green LED beyond its specified norms. But if we only do it for a few milliseconds, we can probably get away with that. But that involves building a LED driver that can put a large energy pulse into the green LED for a very short period of time to get it to create the most intense or the highest number of green photons as possible to come out. So that LED would be fired. In the case of the light pipe, it'd be focused down to the side edge of the diamond crystal, which is shown here by this little pink box. Late in a secondary design, we actually basically move that LED right down onto the stage and put it as close to the crystal as possible. That eliminated the light pipe, so that was a component that we wouldn't need anymore. The other driver, which became fairly complex, is a programmable RF, and specifically a microwave generator with a 2.5 gigahertz center frequency. And we need to be able to have this control system be able to pick a frequency and change it rather quickly. So that those microwave pulses are delivered via a loop antenna around the crystal. And once again, it's finely tuning the type of the energy that you're pumping into those nitrogen vacancy centers. Now, remember from Erica's talk, you use green light to pump up the energy, and then as this crystal would interact with the environment, and in our case, we wanted to interact with magnetic interference. As magnetic interference crosses paths with the crystal, those energy states collapse and they give off red photons. So hopefully those photons we want to measure at the broad surface of the crystal, and they will go up and be collected by a CCD camera. In the original design, we thought we'd use a lens, but the more we looked into it, it became apparent that we could just get rid of the lens and drop the CCC element right down on top of the crystal. So there's like no air gap whatsoever. So the hope is what we would actually get out of this apparatus is a magnetic movie. We might actually be able to see lines of force as they pass over the crystal. That's the hope. We'll have to see what happens. The CCD camera, again, gives information back to the communications processor and would send it up to the workstation where information from that CCD would, if we needed heavy number crunching, nicely equipped laptop would go a long ways towards doing the signal analysis. This particular design for parts came in at $600. It's probably a little higher than that. Again, these days the cost of the crystal went up a little bit. So this was one design, and here's the second.
Okay, so the second design is the pen design. I was thinking of like what are some common things that like students use in school, and like I realized that a pen is like one of the most common things. And so with my design, I have like two separate modules. I have the control module, which houses the Arduino and the microwave generator, along with the laser diode and the beam splitter and the photodiode, and connecting that with the coaxial cable into the pen. The very tip of the pen has a quarter wave resonator that the diamond sits on top of. And so that resonator is made up of a quarter wave transformer and an open stub, and it uses copper wire and copper foil. And so using that, like we are able to get rid of a lock-in amplifier. And so then from the very tip of the pen, it goes back up through a multi-mode optical fiber, which then goes through the laser diode and the beam splitter and the photodiode. And so this pen, the case of the pen can also be 3D printed as well. And so this design came up to be almost $700. Okay. And so the very so for this slide, I had some ideas for like a removable tip. And so we realized that like if there was any possibility for us to, I guess, switch out the diamond and see different types of performances and sensitivities, that like we could do this with my design using a removable tip. And so these are some of the designs that I had for the removable tip. And yeah. And special thanks to the Womanium team and NNL, specifically Verdun and Jasmine. And then thank you to Jesse and Brian for their guidance for this project.
Yeah, I would ditto those handouts of thanks. The Womanium team was pretty cool. So that's basically it. This was a presentation we gave to the National Energy Technology Lab, which is near Pittsburgh, Pennsylvania. The next phase in this project is trying to find a laboratory or a school with a well-equipped electronics lab to take a shot at building these different implementations, taking the designs and going with them. So stay tuned. We'll see what happens shortly. So that's our presentation. So I will stop sharing for a second and open up the floor to any questions on either presentation, or comments or anything.
So Ron, you didn't actually build all this. How do you know it works?
It's all on paper.
Oh, okay.
We basically reviewed, like I said, close to 20 academic papers of people who implemented these capabilities in laboratory environments. There were a couple that got down to some sort of size, but our issue will be whether we can get some sort of performance out of it, because our only mandate here is it needs to be able to demonstrate the phenomena of ODMR. This type of sensor has the potential for magnetic detection to be as sensitive as some of the designs were down in the nano Tesla. Some were even lower, pico or whatever is below pica. Is very, very tiny amounts of magnetic fields that could be sensed by these. If you can sense magnetic fields that tiny, you start getting into the realm where you could be using sensors of this type to measure brain waves. If anybody's ever had one of those, has had to go to a hospital and have an MRI where they shoot you through this big, massive tunnel that makes all sorts of noise and unnerves just about anybody. If you can imagine an MRI which would fit on inside of a helmet, and you just put the helmet on to do a brain scan type of thing. That's the potential for how sensitive these things could be. But yeah, our job was to create a design and based on the information that's out there and the research that's been out there, and see if there was any possible way of getting something that has a potential for being built for under $1,000. Again, we've shown this to the National Energy Technology Lab. They among other people's found it to be something that would be worth pursuing. So our job, our next phase is to find somebody to help us actually build one. So.
So at this point, what kind of muscle would it take to build one? There's there are price constraints on the thing, right?
Yeah.
I guess what I'm asking is how much would it cost? How many people would be involved? How much effort would be on part of a particular company? I'm not volunteering, by the way. I'm just asking.
Yeah. So the cost of the parts is about the only thing I can really comment on. Both of our designs would benefit from, the portable design requires that you build printed circuit boards or build custom printed circuit boards. But with the technology that's around these days, you can order printed circuit boards. You can get, for the size those boards would be, you can get 4, 5, 6 of them for $20, maybe a little bit more these days. It's just a matter of getting the design out to a house that can build them. Same thing with the housings. I don't have any information on what it would cost to 3D print those things, but I know that again in my area, there's at least one library where you can just go in and you essentially pay for the material, something like a penny a gram or something like that. So I don't know at this point what those costs would be, but if you went into full industrial production, there would be additional costs there too. But this is really kind of just focused at being something that if a school wanted to build one, they would have access to those resources, and if they had access to resources and access to off-the-shelf parts, that they would be able to take a crack at it. There's just a lot of fine details that would need to be worked out in for different operational purposes, selecting components like the LED. When people sell LEDs, they don't really care too much about what their center frequency is, whether they're exactly 526 nanometers, I believe it was. So initially we need a laboratory to help with good equipment that can help us remove those any of those questions that we'd have and help us finalize a part selection.
So I think what I'm hearing in answer to my question is that building a prototype would be an effort of sorts, but once
Yeah.
a prototype is made, all the specs are worked out, that somebody could create a second, third, fourth, and 1,000th pretty cheaply.
Yeah, I mean, once the prototype is proven and you've got a solid bill of materials, then it would be much easier for a school of any sort that again had access to a 3D printer and had somebody that knows how to go off and order printed circuit boards, and has lots of volunteer help, so to speak, so that when those printed circuit boards come back, they've got people who can solder the components on as part of their project. It was just a matter of making sure that the design, all the details of the design were hacked out, so we know that it can demonstrate the phenomena. Have any other questions?
Looks like exciting work to me.
It was a lot of fun. Got to learn a lot very quickly. So I would ask my colleagues if they wanted to mention anything about what they got out of these projects.
Ron, can I ask you a question? Sorry.
Sure.
How can I, your contact information, how can I acquire it?
I'm sorry, could you repeat that?
Sorry, your contact information, how can I just get more with your work and moving forward?
If you so I'm the organizer of this meetup group. If you just leave a message there,
Okay,
I will get in contact with you.
thank you very much.
So I'll ask Anjolie, you have any highlights of these projects you'd like to share?
I think, well, all of it.
I
It's
put you on the spot, didn't I?
it's definitely a huge learning curve, especially like because I didn't have like as strong of a background in quantum or math or engineering, and so going through this project, I was like putting in hours trying to just understand. Like it took me like a while just to calculate the length of a wire. And so it was definitely like a huge learning curve, but it was really useful. And so yeah, I think the entire project was fun and helpful.
Great. I'll ask Erica the same question.
I have had a touch of experience playing with the quantum world from various perspectives over the years. This one was new. So it's one thing to be a chemist and to say, I understand nitrogen, I understand carbon. Yes, that was what I studied in school. It is a very fundamentally different thing to say, okay, now that you can model it, what can you do with it? And in that regard, this was opening a door to a realm I had not previously considered, and for this I am grateful.
Thank you. I think for me, it was just the wonder of learning a technology I'd never heard of before. And then finding out that all sorts of past learned technology could come to bear to make it useful. So hopefully we'll see what happens as time goes on. All right.
It's a very exciting field for a variety of reasons, not just the buzzwords quantum computing. That's the one that gets a lot of the press attention, but the world of quantum sensing is arguably more applicable, at least today, in the immediate, right now, going on around us sense. Quantum computing gets more attention, but in some ways it is still just out of reach. So
yeah, and we barely scratched the surface
Oh,
on
yeah.
the different kinds of sensors. We were fortunate to learn about gravimeters based on atoms floating in a vacuum. Again, stuff I never was ever exposed to. Just a phenomenally interesting technology. So, do we have any other questions from the audience?
we don't bite too much.
Right, going once. Okay.
Thank you
It's
for
not
your
enough.
time.
Yeah. Once again, I'd like to thank my colleagues, Erica and Anjolie, and so happy you guys were able to come and participate in this. And thanks to everybody who showed up. And I hope everybody found this as interesting as we have going through the process. So thank
And thank you,
everybody.
Ron, for coordinating this, and thank you, Mr. Bird, for recording and hosting.
Thank you,
Yes, thank you.
Thank you, Ron. Thank you, Erica. Thank you, Anjolie.